Okay, so let's start. For the activity 2, I will just grade the reports myself. So I think you all have a heavy workload, so I won't let you do the peer evaluation anymore. So let's continue with testing. So last time we said even for the toy example of a 20 times loop, it has so many different possible execution paths that it takes many years to exhaustively test this program. Therefore, exhaustive testing is not possible for any realistic program. That's why you need to plan tests to design tests to have the highest likelihood of uncovering defects with the minimum amount of time and effort. Up to 40% of project effort is devoted to testing. So a test plan includes a testing strategy, the criteria and goals of testing. When do you stop testing, essentially? What kind of tests to perform, white box, black box, regression testing, and others, and the coverage you need to achieve, and the percentage of tests that should pass. And based on the strategy, you estimate the resources required, including people, resources, how many engineers, and also monetary budget. And then you design a schedule for the testing. So first we discuss the test engineer. So the plan tests we won't discuss in detail. That's just one slide because we don't have a concrete project. We don't have a large-scale project as an example. So we just start from a small scale and see how you design tests given a piece of code. So a test case is one way of testing the system. So it is one input you can provide to the system and to observe its output. So it specifies what to test, expected result, under what conditions to test, and how to test. So there are essentially three types of test cases. White box tests is testing in the small, that is, test cases that verify component logic based on data control structures. Availability of source code is required. It really should be a term that's clear box tests. That is, the box is transparent. You can see inside of the source code. So it's based on the knowledge of the internal workings of a component. Knowing the internal workings, we can design a set of test cases to test different execution paths through the source code. Black box tests is so-called testing in the large. That is, they verify component functionality based on inputs and outputs only. Availability of source code is not required. So notice the difference here. The white box tests are testing the component logic, while black box tests are testing the functionality. Even though they look very similar, so black box tests doesn't care how the component is implemented internally, as long as the input and outputs are correct. While the white box tests really would look inside of the source code and follow the control flow and data flow. So they are based on knowledge of a specified functionality of a component. If a component is a sorting operation, then if you pass it to the unsorted array, it should return you a sorted array. So as long as the array is sorted, whether it's implemented as quicksort or bubble sort, doesn't matter to the black box tester, but it does matter to the white box tester. Regression tests is the selective white box and black box testing, combination of both, retesting to ensure that no new defects are introduced after a change is made. So, because sometimes when you update the system by adding new functionality or fixing a bug, you may introduce new bugs. Therefore, regression tests are designed to rerun old tests, and perhaps designing some additional tests to ensure that any change you made to the system does not introduce additional bugs. So it can be either white box or black box. So documentation of a test case includes test case name, description, what the test is designed to do, target class component subsystem name. So the target of your test can be a class or a component or a larger subsystem. So name of the thing to be tested. The thing is a general term to refer to any class component or subsystem. Target a class component subsystem operation. So name of the operation to be tested. Test type, white box or black box. Valid, invalid input. That is, if you pass, some tests are designed so that you pass invalid input and you get back a valid output. Some tests are designed so you pass the invalid input and see how the program behaves. If the program crashes, of course that's a failure. So ideally, this program should tell you that it's an invalid input. So test values, that's the input values to be used for the test. And finally, verification, that is compare the result with the expected result and decide if the test passed or failed. So white box testing, the goal is to design selective tests to ensure that we have exercised all independent paths in the code at least once. That's called basis path testing. Or all logical decisions on their true and false sides. That's called condition testing. Or all loops at their boundaries and within their bounds. That's called loop testing. Or internal data structures to ensure their validity. That's called data flow testing. To try to follow the definition and use of variables. So these are 4 types of white box testing with different criteria. So each one they may be used. Different types of white box tests may be used in combination for a single piece of program, because they each type may have a better chance of finding some types of bugs. So data flow testing is good for finding bugs related to data structures, while perhaps condition testing is better for finding bugs caused by conditional control flow, if then else, or while loops. So why not just statement testing? That is, if you have a program and you have covered every statement in the program. By covered, I mean you have executed each statement at least once and observed the result to be correct. Now, that's not enough. So for this example, statement testing is enough. So this program, this is a flowchart. I equals j plus 1. The equal means assignment. If this a and b is true, you go to the right branch. If it's false, you will do nothing. Go to the left branch. and finally you execute n equals p plus 1. So if you follow the true branch in this program, then you have tested all 4 statements. So, and then if the program result is correct, it should be okay. So because the false branch doesn't have any statements, so if you follow the left branch, you execute 3 statements, which seems to be redundant, right? You have covered all 4 statements by following the right branch. Why do you want to try the additional left branch? So for this example, it's indeed not necessary to follow the left branch, but for another example, you need to follow both branches. So here, I equals 0 initially, and if a and b is true, then I equal 1. Otherwise, you do nothing. And finally, you have x equals y divided by I. So if you follow the right branch, you get a correct execution of the program. But if you follow the left branch, you get a division by 0 error. Therefore, you need to follow both branches, even though following the right branch alone has already covered all the 4 statements. That's why statement testing is not enough. You need to really cover the different paths in the program, even though all these paths may cover the same statements. So even though the false branch executes no additional statements, it needs to be tested. So basis path testing, the goal is to exercise each independent path at least once. So the steps are, first, from the code, you draw a flow graph. Flow graph is a higher abstraction level of an activity diagram. So you learn that activity diagrams can be used to express the internal implementation of an operation. In addition, an activity diagram can be used to describe high-level operations, high-level control flow of the entire system. But we're discussing activity diagram now for its application in describing the fine-grained operation implementation. So draw the flow graph based on the activity diagram, or perhaps draw it directly, and determine the cyclomatic complexity of the flow graph. This is the graph theoretical concept to help you to design the basis path tests. Determine a basis set of linearly independent paths which should be equal to the cyclomatic complexity in terms of the number of paths. Prepare test cases that force the execution of each path in the basis set. So, and finally compare the results. So a flow graph, each circle represents one or more non-branching circle statements. So non-branching means that if you have a block of statements, there's no internal branching within the block. There can be branching at the top and at the bottom, but inside this body of statements, you shouldn't have any if then else, or while, or for loops. So, so each of the black circle represent is also called a basic block in testing theory. So this is a sequence. This is the if then else, where this thing is perhaps the if statement, and in combination with all the statements before the if. And one is true branch, one is false branch, and this thing is the collection of statements after the basic block after the if then else. And case is a generalized if then else. You have more than two branches, and do while, do until. So do while is do something while a condition is true. So that is, you may jump directly to the end if the condition is false in the beginning. But do until is do something until something becomes false, then you stop. Do until executes the loop at least once. So that's the difference between do while and do until. This is the keyword in older programming languages like Pascal. But I think the modern languages don't have do until anymore. So here's one example program. Process records, perhaps a database application. Do while records remain. So you iterate over all the records. Read the record. If record field 1 is 0, store in buffer, increment a counter. Else, if record field 2 equals 0, reset counter, and else store in the file. So essentially this is counting how many records with field 1 equals 0. And whenever you encounter a record field 2 equals 0, you reset the counter. And if the record field 2 is not 0, then you can store the information in the file. So essentially it's doing some counting. The exact functionality is not important. So we draw the activity diagram for it, where each node represents a statement. So node 1 is the if then else. Do while records remain. So essentially it's checking that if this records remain condition is true, then you go into the loop. Otherwise you jump out. So it's doing a condition checking. If it's false, you jump out to 13. Statement 13 is this guy, and do. Otherwise you jump in and execute 2. Statement 2 is reach record, and then followed by if then else. So statement 3 is the if condition checking. If it's true, you execute 4 and 5. If it's false, you do another condition checking for the field 2 equals 0 or not, and then you do if it's false, you do from 7 you go to 8, reset counter if it's true. Otherwise you go to 9 and 10, store in file. So essentially this program has 3 positions where you check for a condition and make a decision as to whether to go left or right. And finally, at the end of the while loop, you go back to the initial condition checking. That's the do while statement. So that's the activity diagram. The flow chart, the flow graph is obtained by grouping the basic blocks, that is grouping statements with no internal branches into a single node. So that is, you group, say, 4 and 5, no internal branching, so they are in the same basic block, and 6 and 7 are in the same, 9 and 10. So 8 is in its own node, and 11 is in its own node, and 12 is in its own node. Finally, 13. So you get a flow graph, which the reason you define the flow graph this way is that it's because you want to focus on the conditional control flow behavior, not the sequential functionality behavior of the code. That is, even perhaps on this branch, even if you execute 1,000 statements, as long as there's no internal branching within the 1,000 statements, you treat it as a single node. You only care about when there's a branch in the code caused by a conditional control flow. So by grouping the statements this way, you reduce the complexity of the graph. So here's the flow graph after grouping the activity diagram nodes together. Now it's really a high-level skeleton that shows the control flow only. Here's the flow graph node to program statement mapping. Each flow graph node corresponds to one or more statements. Cyclomatic complexity is a quantitative measure of the logical complexity of the code. So it's a logical complexity, meaning that it measures the control flow complexity, not the computational complexity. You may be doing a very complicated algorithm of signal processing in the code, but if you have very little branching, conditional branching, then you have very low cyclomatic complexity. So it provides the upper bound on the number of paths that need to be tested in the code. So this comes from graph theory. You have three ways of computing the cyclomatic complexity of V. So this is the notation where G represents a graph and V represents its cyclomatic complexity. You can count the number of regions. A region is an area bounded by nodes and edges. Also, an area outside of the graph is also a region. It's easy to miss that region. So, or the number of edges minus the number of nodes plus 2, or the number of single predicate nodes plus 1. So simple predicate is a if statement with a single predicate inside. That is, if A, then something. That if is a simple predicate, but you have a complex predicate like if A and B or C. That's a complex predicate that counts as 3 simple predicates. So for this guy, the cyclomatic complexity is 4 by region counting. You can count 1 region, 2, 3, and finally there's the whole region outside of the graph. That is region 4. Region 4 is the whole region that's here. That counts as 1 region. So therefore, the number of regions is 4. Or you can count the number of edges and nodes. You have 9 nodes and 1, 2, 3, 4, 5, 6, 11 edges. So if you do it the other way, 11 minus 9 plus 2, number of edges minus number of nodes plus 2, that's also equal to 4. And also number of simple predicate single predicate nodes plus 1. How many predicates nodes do you have? You have this guy is a predicate node. So whenever any node has 2 or more outgoing branches, it's a predicate node. And this guy is another predicate node, and this guy is another one. So then you have 3 predicate nodes plus 1 is 4. So all the 3 different techniques for calculating the cyclomatic complexity always yield the same result. Then you determine a basis set of linearly independent paths. So an independent path is any path that introduces at least one new set of processing statements or a new condition. If a path crosses only the statements that have been covered before, then it's not an independent path. So basis set is the set of independent paths through the code. So the basis set is not unique. You may have multiple basis sets which are different from each other, but the size of the basis set is always the same. You may have three paths that covers that's a basis set. Another 3 paths is another basis set. They may be both valid basis sets. So they're not unique. So we'll see some examples later. Test cases derived from a basis set are guaranteed to execute every statement at least one time during testing. So cyclomatic complexity provides an upper bound on the number of independent paths. That is the size of the basis set. So it's an upper bound, but in all the examples we show in this lecture, it's equal to the number of basis paths. And in most cases, it is equal. So let's count the number of independent paths in this program. This is the activity diagram. So you can also do it with a flowchart. It wouldn't make a difference. So this is 1, 2, 3, 6, 7, 9, 10, 11, 12. You follow until the end. So this is another one, the green part, where the node 7 takes the true branch. And this is another one, the blue paths, where node 3 takes the true branch. And so there's another one which is not very obvious. So this is when from 1 to 13. So this is the when the node 1 takes the false branch. So in this case, you have 4 independent paths. That is, the basis set has size 4, which is equal to the cyclomatic complexity. So independent path, as I said, is any path that includes at least one new set of processing statements or a new condition. If you look at this path from 1 to 13, statements 1 and 13 have both been covered by the other basis set, by the other independent paths. So the reason why 1 to 13 is a new path is because it introduces a new condition. That is, condition 1 equals false. Even though the both of the statements have been covered, the condition is new. Therefore, it's a new path. Finally, you design test cases that force the execution of each pass in the basis set. So to do that, you just pick the inputs to force the each of the conditional nodes to take a different direction. So that may not be easy, because the conditional nodes, the conditions may not be the direct inputs. You need to tweak the inputs, and perhaps after going through many statements, you reach a conditional node and somehow force that node to go left or right. So activity diagram is not needed, but the picture will help to trace the program paths, so that you know exactly which of the conditional checking node need to be forced to take the left or right branch. Count each logical test. Compound tests count as number of Boolean operators plus 1. So a logical test is the test of if then else, or do while, or for. A for loop is also introduces a logical test, because for can be rewrote as if and whiles. So as long as you have more than one branches coming out of a node, that's a test. And compound tests count as number of Boolean operators plus 1. So if you have if A and B or C, then you have 2 Boolean operators and or plus 1 is 3. Therefore, it's equal to the number of simple predicates. So just to make it more clear, so if you have A and B or C, then this is a compound test that really consists of 3 simple predicate testing. So each one is a simple predicate, A and B and C, and you need to force A to be true or false, B to be true or false, C to be true or false. Not just the whole thing to be true or false. That's not sufficient. You need to force each one. Basis path testing should be applied to all components if possible, and to critical components always. That is, if applied to all components is too expensive in terms of time and resources, then you need to do it for the critical components. So basis path testing does not test all possible combinations of all paths through the code. It just tests every path at least once. Notice the difference between these two. So let's go back to the early example. We saw where we calculated how many possible paths are there through the code. So for this example, how many independent paths do you have? You have 1, 2, 3, 4, 5, right? You have 5 independent paths. But the number of all possible combinations of all paths is 5 to the 20th power. So what basis path testing is to test each of the 5 paths, but not all of the 5 to the 20th power combinations of paths. So that's not possible. So here's another example. A student can register for a course. So this is gets translated into this code with 1 compound condition testing with 4 simple predicate conditions. If all of these things are true, so enrollment is open and student does not have exclusions, and parentheses student has prerequisites or student has permission from the instructor, then if this compound condition of and or is true, then you can register. Otherwise, you cannot. Excuse me. So, if you draw the activity diagram, you have the statement 1 gets turned into 4 condition testing statements: 1A, 1B, 1C, 1C, and 1D, because it's a compound condition testing. 1A is enrollment is open or not. 1B is student does not have permission, exclusions or not. 1C is when student has prerequisites or not, and 1D is student has permission or not. And if you fall here, you get to here, it means that the student can register. And if you get to here, the student cannot register, and registration fails. And finally, you merge to the end. So let's look at the flow graph. The flow graph is a merge of the activity diagram nodes. So now you have the flow graph where the node 5 is a combination of statements 2 and 3, and node 6 is a combination of statements 4 and 5. So you have how many regions? You have 5 regions. 1, 2, 3, 4, and 5. Don't forget region 5 is the one outside. There's always the one outside the whole graph. So the cyclomatic complexity is 5. And you can work out the basis set, look for the independent paths. 1, 2, 3, 5, 7, that's 1. 1, 2, 3, 4, 5, 7. 1, 2, 3, 4, 6, 7. 1, 2, 6, 7. 1, 6, 7. So it's getting messy. So each basis path represents one possible different decision on the decision nodes. So you can find out which nodes are the conditional testing decision nodes by looking at how many outgoing branches it has. So 1, 2, 3, and 4 are all conditional testing nodes because they have 2 outgoing branches. The others all have 1 single outgoing branch, and you should follow the both of the branches at least once when you design the basis set. So any questions on that? So each of the basis set is essentially, so 1 is enrollment is open, student does not have exclusions, and student has prerequisites. And statement basis path 5, enrollment is closed. So let's look at basis path 5, 1, 6, 7. So it directly falls from the false branch from node 1 and goes to if the registration is closed, then you don't check anything else. You just go directly to failure. So as we see this example, essentially one statement can turn into multiple nodes in the flow graph. that is when the condition testing is a compound condition. And also multiple statements can be merged into a single flow graph node. That is statements that don't have internal branching. So video cells consider this procedure. Reserve video copy if status is available or status is granted, and return date less than equal to request date. That is, you can request a reservation at a future date, not immediately. If the rental video copy is currently rented, but its due date is earlier than your requested reservation date, you can still reserve it. The status is reserved, and link video copy instance to member instance, result equal to success. So immediately you can see that these three statements can be merged into a single flow graph node because there's no internal branching. And else result equals failure. So draw the flow graph. So you can start with the activity diagram, or you can directly draw the flow graph. So let's start from the activity diagram. So again, statement 1 gets mapped into 3 nodes, 1A, 1B, and 1C, because it's a compound condition. And 2, 3, 4 gets mapped into a single flow graph node because it has no internal branching, and 5 and 6 gets mapped into a single node, and finally 7. So notice that we are using a programming language where you have if and if. So this is perhaps the syntax of Pascal in some earlier languages, but if you have C or Java, you don't have and if, right? You only have a open parentheses, close parentheses. So in that case, you should draw a flow graph node, say 7, representing perhaps the close parentheses, even though it may not occupy a separate line, just to indicate that it is a distinct location where control flows merge into a single control flow. So common errors are that missing the outside region. So when you count the number of regions to calculate cyclomatic complexity, you should always remember there's an outside region. Missing including a node for last statement. So that's what I said. If you have the last statement as and if, you should put it in there. Even if you don't have, you should count the close parentheses as the last statement. Having a condition with one outgoing branch. A condition, by definition, condition node has 2 or more outgoing branches. If it's an if, or while, or for, it has 2 outgoing branches. If it's a case statement, it has 2 or more outgoing branches. Draw an activity diagram. So you can draw it as a aid to help you to draw the flow graph, but at the end you should draw a flow graph. When you're asked in the exam to draw a flow graph, don't draw an activity diagram. That is, you should merge all the sequential statements without control flow inside into a single node. Draw a state machine diagram. That's a common error, and not understanding what is a flow graph. So more on basis path testing. One more example. You have the first 5 statements. You have one if then else, and then you followed by another if then else. So this flow graph looks like this. One if then else followed by another one. So notice that statement 4 is really a merge of previous one's and if and this one's if. So so this is a basic block because the branching happens at the end of the block after the if, not within the two statements. So the cyclomatic complexity is 3 because it has 3 regions, right? 2 inside and 1 outside. How many independent paths are there in the basis set? Independent path is any path that introduces at least one new set of processing statements or a new condition. So in this case, it has a 2. So it can be a 1, 2, 4, 5, 7, both following on the left, and or 1, 3, 4, 6, 7, both following the right, or it can be another set is 1, 2, 4, 6, 7, or 1, 3, 4, 5, 7. So as we said, the cyclomatic complexity is the upper bound on the number of independent paths. So it doesn't have to be necessarily have to be equal to. So in this case, you happen to have 2 independent paths, but not 3. So let's look at perhaps how about this one 1, 2, 4, 5, 7. And 1, 3, 4, 5, 7. Does that form a basis set? So 1, 2, 4, 5, 7, and 1, 3, 4, 5, 7. So that is not a basis set because statement 6 is not covered, and condition 4, one of the branches is not taken. So but if you take 1, 2, 4, 5, 7 and 1, 3, 4, 6, 7, then all the condition branches are covered and all the statements are covered. So that's a basis set. So when you're designing a basis set, always remember that all the paths in the set should cover all the statements and should exercise all the true-false branches. So this example just shows your basis set is not unique. You can have multiple valid basis sets. So V is the cyclomatic complexity is the upper bound on the number of independent paths. So condition testing further exercises the true and false value of every simple logical condition in a component. So that is more exhaustive than basis path testing in terms of covering the conditions. We'll see why. So errors in the condition can result from errors in simple conditions where A, relative operator B, where relative operator is all the possible ones, may be negated with not. That is, if a condition should be A less than or equal to B, the programmer may make a mistake and say not A less than or equal to B, i.e. A greater than B. So you need to detect possible errors caused by programmer errors like that. Compound condition, 2 or more simple conditions connected by and or. So you may make a mistake in the and or part. So relational expression is this is the simple condition involving some arithmetic expressions. So A times B plus C greater than 8 plus B plus C. So you may make an error inside of each of the arithmetic expressions right? You may say you may accidentally type in a double star b, which means that it's a to the b's power instead of a single star b, and you need to detect that kind of error as well. Also, Boolean expression, so non-relational expressions, that is single thing, single Boolean condition negated with not. So many errors can happen in these conditions. You can make an error in the Boolean operator. That is, in these operators, you may mistype greater than instead of less than. You may make an error in the Boolean variable here. You may make an error in the Boolean parentheses. That is, you may forget to add a parentheses if you want or to have higher precedence than and. You may have error in the relational operators or arithmetic expressions. So to detect these errors, you need condition testing. So here, for branch testing, if you have a compound condition, then you test for first the compound condition as true or false, then each of the simple conditions as true or false. So this is already covered in the basis path testing. So, but we'll see some examples not covered by basis path testing. So domain testing is something that's additional to basis path testing. So if you have an expression E1 relational operator E2, where you have relational operator is greater than, equal to, and less than, so you should use values that make the E1 greater than, E1 equal to, and E1 less than to detect relational operator errors if E1 and E2 are correct. That is, for example, if you have say if you have E1 greater than E2, so normally you should make it true or false, right? You can just check for one case where E1 is greater than E2, another case E1 is less than E2. But domain testing says you should, in addition, you should try E1 equal to E2, even though it yields the same conditional result as the E1 less than E2. The reason is that you want to detect errors. So if E1 and E2 are complex expressions, and perhaps the boundary condition happens at the equal sign, so you may not detect it if you do not try the equal case. So to detect errors in E1 and E2, the difference between E1 and E2 for the tests that make E1 greater than and E1 less than E2 should be as small as possible. That is, if they're integers, you should try to make them to be off by 1. If they are floating points, you should try to minimize their differences. The reason is that the smaller the difference is, the more likely you're going to encounter the error condition. It's not a guarantee, of course. So the theory is that if the difference is small, it's likely that if there's any errors, it may come up by crossing the Boolean condition from true or false, or from false to true, and then you can detect it. If you have a larger difference, then perhaps you mask any possible errors. So loop testing is to test loops at and within their bounds. So you have say a simple loop. You should try these 5 cases. First, you skip the loop entirely. That is, you jump directly from the loop head to the loop end without executing the loop body. Or you do one pass through the loop, or 2 paths through the loop, or n passes through the loop, where m less than n is the number of iterations in the loop, or n minus 1 and n plus 1 passes through the loop. So n plus 1 passes is error condition. So if you try to pass in a loop bound of n plus 1 and see how the loop behaves, it should give you some error message. So now you see these two types of loops. One is to you must execute the body at least once. One is you can jump over the body directly to the end. So the reason you design these 5 different ways of testing the loop is that these are likely to be to detect errors based on people's experience. That is, you're testing really the both the average case and the boundary cases. For nested loops, where you have one loop with the inner loop, so you start from the innermost loop, conduct simple loop tests based on the 5 cases we discussed before, while holding the outer loops at their minimum iteration values. So that is, if you have a for loop of I equals 1 to 100, and inner for loop of j equal to 1 to 100, then you hold I equal to 1 while testing the inner loop. And then work outwards, conducting simple loop tests for the next innermost loop. Continue until all the loops have been tested. So in this way, you if you have say 2 nested loops, then the number of tests you conduct is 2 times the tests you conduct for a simple loop. Obviously, it's not an exhaustive test. If you had an exhaustive test, it's really the square of the test of a simple loop. But that's typically not feasible for any large system, so we do this. We conduct simple loop tests while holding the outer loops at the constant minimum value to instead of varying the outer loop for all possible values. That will involve too many test cases. So tests grow geometrically if you do that. At the level of testing increases. So concatenated loops is when you have independent loops and they're concatenated together. That is, we saw one case before where you have if then else followed by another if then else. If the loops are independent, that is, the second loop's iteration variable does not depend on the first loop's iteration variable, then you can use simple loop testing to test each one separately. If the loops are dependent, that is, if one loop depends on the variable set in another loop, perhaps the first loop sets the iteration bound for the second loop, then you should use the nested loop testing, treating the second loop as the inner loop of the first loop. Unstructured loops so in this case, it's just a bad design. So you should not have unstructured loops. So redesign the code is the solution. So these loop tests are designed to have the highest likelihood of uncovering errors with the minimum amount of effort and overlap of tests. So obviously, these are highest likelihood is a heuristic statement. That is, it comes from experience. There's no guarantee that you uncover any possible errors. So data flow testing is to ensure that the value of a variable is correct at certain points of execution in the code. So in the previous, all the testing methods we discussed are control flow testing. That is, you're focusing on the different paths through the program by trying all the true-false branches of the conditional testing nodes. So you don't really. So now this focus here is different. This is focusing variable values and if they're correct. Select test paths according to the locations of definitions and uses of a variable. So the definition of a variable called def s. S is a statement that contains the definition of variable x. Use s prime, where s prime is a set of statements that contains a use of x. And def use chain is the set of variable statement of def statements and use statements where x is live, that is not redefined between s and s prime. So what is a def? A def is something like, say, x equals 2. That is a definition of x. Notice that it's not a declaration. If you have int x, that's a declaration, not a definition. Definition is assignment of a value. Use is perhaps y equals x plus 1. That is a read, a use of x value. And if all the intermediate statements in the middle do not redefine x, that is, x value stays 2 throughout the paths, then this path here from x equal 2 to 2 to y equals to x plus 1 is a def use chain. That is from definition of x to use of x. But if you have something in the middle that says x equals 0, then the def use chain should go from the latest definition to to its use. So that is when we say x is live, not redefined between s and s prime. Then this s to s prime is the def use chain. So a testing strategy is that every def use chain should be covered once. So for every variable, do a test along the path from where the variable is defined to the statements where the variable is used. The test can be combined with basis path testing. So so this data flow testing is really orthogonal to basis path testing, in the sense that remember, basis path testing really ignores all the linear sequences of code without internal branching. For basis path testing, you're really treating it as a single node. But for def use chain testing, you should really look inside of the sequential statements and see which statement actually defines which statement uses, and try to test all the def use chains. So it's really testing the sequential code as well as the conditional code, conditional branches, because the def and use may span several conditional nodes from on the def use chain. You may have multiple conditional testing nodes. So it's different from basis path testing, but it can be combined with it. So all the testing methods up to now has been white box testing, because you require source code available. Otherwise, you cannot know what the flow graph is and how to do the data flow testing. So now black box testing is when you treat the code as a black box, and issue inputs to it and observe actual output from it, compare it to the predicted output, that is the correct output, and see if they're equal or not, to see if the test passes or not. So the code can be executable code only. That is, the tester may only get an exe file, not the source file. So black box tests attempt to find incorrect or missing functions. That is, if you have a sorting operation as your executable, and you pass in the array, and the result is not sorted, then it's incorrect, right? Interface incompatibility errors. That is, if your program should expect to receive a certain data format, and you pass in the format, and if it cannot read it, it's an interface incompatibility. Data structure or external database access errors. That is, if you perhaps run the program for a few days and check the database. If the database has any inconsistencies or dangling pointers,